Okay, so in the previous segment of this lecture, we gave the basic definition of the language modeling problem. And in this segment, I want to talk about trigram language models, which, as I said before, are an extremely important and widely used type of language model. So trigram language models build heavily on the idea of Markov processes, which are a very important concept in probability and statistics. So let's first talk about Markov processes, and then we'll describe how we can use them to construct a trigram language model. So in a Markov process, we have the following scenario. We have a sequence of random variables, x1, x2, up to xn, and each random variable can take any value in a finite set V. For example, V might be the set of words in the language which we're interested in. And for now, we'll assume that the length n is fixed. So every sequence has the same length. For example, we might have every sequence having length 100. We'll first cover this case where the length is fixed, and then we'll go on to generalize this to allowing n to vary, allowing the value for n to itself be a random variable. But for now, n is fixed. Our goal is to build a model of the joint probability of x1 taking some value little x1, x2 taking some value little x2, up to xn taking some value little xn. And each of these values is in the set V. Okay? So we have a joint probability distribution over the values of these n variables. It's worth noting that there are a huge number of possible values, x1, x2, up to little xn. In fact, if we have a vocabulary V whose size is size V, as I've written here, there are size V to the power n different possible sequences. And so we have a distribution over this very, very large set of possibilities. That's because I have, if I think about the first position, I have V possibilities here. If I think about the second position, I have V possibilities here. And up to the nth position, I have V possibilities there. And so I end up with V to the power n. Okay? So how do we go about modeling this joint probability? There's basically going to be two steps in deriving what's called a first-order Markov process. And the first step is to use the chain rule of probabilities to decompose this entire expression as a product of expressions. Let me explain a little bit about what's going on here when I say we're using the chain rule. So remember, if we have events A and B, and we want to say what's the joint probability of events A and B happening. For example, we might have the joint probability that x1 is equal to little x1 and x2 is equal to little x2, just considering the first random variables in the sequence. Then the chain rule says the following, that I can decompose this into a product of two terms. The first one is P of A, and then I multiply that by the conditional probability of P of B given A. And this follows directly by the definition of conditional probabilities. And if we apply this to this very simple case where we have a sequence of length 2, this means I can decompose this as the probability that x1 takes the value x1, multiplied by the probability that x2 takes the value x2, given that x1 is equal to x1. Okay? So that's the chain rule applied to just two events, and we can apply this to longer sequences. So if I have the joint probability over three events, A, B, and C, chain rule says I can decompose this as P of A times P of B given A times P of C given A and B. And so notice we have first the probability of A, then the probability of B, then the probability of C. and at each point we condition on the previous events in this particular sequential order. And again, we can apply this to a sequence of length 3. So if I have this expression here, this can be written as actually exactly what I've written up here. This is the same times p of x3 equals x3 given x1 equals x1 and x2 is equal to x2. Okay, it's important to realize that this kind of decomposition using the chain rule is exact. I can always take the joint probability of 3 events and decompose it in the following way. So what I've written here is simply this chain rule applied to the full sequence of random variables x1 through xn. It's really a generalization of these two cases I've shown you here for arbitrary n. So the first term is p of x1 equals x1, and then I have a product of terms, one for each position from I equals 2 to n. Each term has the probability that xi equals xi, and I condition on all of the previous values for the random variables in the sequence. And again, it's critical to realize that this equality is exact in that I can always take a joint probability of this form and rewrite it in using the chain rule in this form. So that's the first step in deriving a first-order Markov process. Now let's go over the second step. And here is where we make, critically, the Markov assumption. Okay, so again, this equality is exact, and this equality follows by the Markov assumption. So what is that assumption? And it's a first-order assumption. We'll see why we call it first order in a second. But this is just saying that for any position I in the range 2 to n, for any sequence x1 through xi, the probability that xi is xi, given these previous values in the sequence, is equal to the probability that xi equals xi, conditioned on just the previous value at I minus 1. So we've essentially made the assumption that this random variable at position I basically depends only on the value for the random variable at I minus 1. To be a little more precise, this independence assumption is saying that this random variable is conditionally independent of all the previous random variables once I condition on I minus 1. So everything up to I minus 2 is irrelevant. And that leaves us with this expression here, where we say that the joint probability over this sequence is equal to a product of terms. I have p of x1 equals x1, and then I have a product from I equals 2 to n, and at each point I have the probability that xi is equal to little xi, given that xi minus 1 is equal to xi minus 1. Okay, so this is clearly a huge assumption. I'm just assuming that each random variable depends on the previous value. But it's going to be very useful in that it considerably simplifies the model, and as we'll see, it considerably simplifies the number of parameters in our underlying model.